exchange with Marco, so you have some. You didn't read well the time, so he was online 1 hour later, and he was expecting us there. So he did the talk at 4 p.m. So the schedule will continue as it is. So we have the pleasure coming here, Pepe Jose Seade, one of Nigel's earliest students, and among the many things Pepe did, I want to highlight that he's now the president of the Mexican Academy of Sciences, many other things, but now he's the president, and his main job. So thank you.
I'm very, very happy that you're able to be in this talk. So when I came close to 1976, Michael had just had a few years of coming back from his training. The state was box training that we started. And I wasn't first student of Nigel, but I started with someone else. But then, like many football players, after a certain time, I changed to a better team. And I started working with Nigel. And I came to him with the problem which I was worrying was a problem that came from my topology, and I was approaching my next theorem. I have managed to get so problems that I was absolutely stuck. I didn't know what to do. And then I kept analyzing the problem that I was trying to do. It worked for some minutes because, I don't see how you're going to solve the way you're doing it. And I said, I knew. He said, what if we think of it in this way? He changed it completely and translated it into a problem in singularity theory and Fuchsian. And then progress started, and I became working with Nigel, of course, and also the singularity theory and Kleinian groups. And those are the two lines of research that I've been following ever since, I think, 40 years. So today I'm going to speak about something that we could call Kleinian groups in several complex variables. So let me start from scratch. Yeah, thank you. Okay, so let me start from scratch. Here are the important things that probably you all know. We'll go quickly. So Kleinian groups were introduced by Enrico Poincaré at the end of the 19th century. They were by definition groups of model transformations. And well, at first he had one more thing that I'm going to say that something which is called the limit set, I go to that, was not the whole sphere. But later the condition was removed, and discrete groups were, Kleinian groups were discrete groups of model transformations. And we all know that well, every such the set of these transformations can be identified with a two matrix, and two matrices by central formation, they differ by multiplication by -1. So this is the projective group, which is isomorphic to the group of orientation to certain conformal automorphisms of the Riemann sphere, which is the same as isometries of the hyperbolic direction of the space. And if we restrict to real coefficients, we have these isomorphisms. This is the group of isometries of two-dimensional hyperbolic space, which is the same as the holomorphic isometries of the complex one-dimensional space, which is also this group. So we have all these things. Almost each item here is a whole area of mathematics, and all these isomorphisms bring a tremendous richness to the subject. So this has been a subject in which there have been tremendous results for decades and decades and decades. And one could speak about that for long time. Now, whenever one has such a group, the limit set is by definition the set of accumulation points of the orbits. we take a Riemann sphere or CP1, and you get the group action, and you look at all of it, you see what we get in late, and that's the Kleinian set. This is by definition a closed invariant set, and the group is infinite, then it's trivial to see that the set is non-empty. So because if you take any orbit, you have a sequence in a compact space that has conditions. So it's a non-empty closed invariant set. This complement, by definition, is called the rhythm of discontinuity. It is the largest set where the action is properly discontinuous. That means that if you take any compact set and you look at the solid, it intersects itself in at most finitely many images of the orbit. This is also the largest set where the action is continuous. And so if we look at the limit set, it is here. So you have a group of transformations of CP1, you have this closed invariant set, which can be very complicated, very interesting, and it is there that the dynamics concentrates. The action on the limit set is minimal, that means that every orbit is dense. And if you look at the complement, then it is very beautiful action for very tame, so to say, good for geometry. So there's reducements, and it is natural to look for generalizations to higher dimensions. And then what does higher dimension mean? Because on CP1 is the same as hyperbolic three-space.
Sorry.
CP1 is the same as hyperbolic three-space, the same as conformal automorphisms on the sphere. But there's also holomorphic transformorphism of CP1. In higher dimension, we could be talking about conformal geometry, which is the same as real hyperbolic geometry in one-dimensional. Okay. But it can also mean groups of projective automorphisms on CP1, on CPM. So this side has been explored by many authors, and there's a lot which has happened and is happening. I will focus on the second aspect. So this is a line of research which I started working in the 1990s with Alberto Berkowski, and then we have continued in Mexico with a group of people. Here are some names, and so I will focus on that. Discrete groups of projective transformations. Just to try to convince you, it can be interesting, because this group contains the affine group. It contains also the group of holomorphic isomorphies of complex hyperbolic space, which actually this atom projecting space presents a ball. And that ball serves as model for complex hyperbolic geometry. So then they are somehow the equivalent in higher dimensions of function groups. Function groups, by definition, are discrete groups of transformation, of model transformations that preserve a ball in the sphere. Okay, so this could be thought of as playing this role of function groups within here. Well, we can also look at the productivization of the balance groups. We can look at real hyperbolic assembly groups. This group is isomorphic to this one, and this has an actual model in here. So groups of real hyperbolic assemblies have a natural embedding into this setting. But there are also many other ways to embed these groups here. One of them is, for example, looking at the complex version of the Hitchin representations. They give you natural embeddings in here. And there are many other families of examples. Okay, so looking at these discrete groups here unifies several areas of mathematics. Let me start the discussion with a couple of examples. Those were our original examples. That's how we enter into the subject. One comes from using Christoph Florida, was already mentioned, I do know better than I. So we recall that the Penrose program starts with a beautiful interplay between the conformal geometry of conformally flat manifolds and the complex geometry of the crystal spaces. And the most basic case is when we have four-dimensional sphere that already appeared in the previous talk. So we know that we can think of it as being the space of quaternionic lines. And that means we can think of each polynomial line as a plane, a complex plane in four-dimensional complex space. So we have a natural projection. These are the complex lines in C4. These are the polynomial lines in C4. So there's a natural projection, and the kernel is CP1. The complex lines in the polynomial line. Okay, this is a beautiful twistor-Calabi configuration, and the fiber is CP1. And we know, as a basic point in the previous problem, that this group of conformal transformations here has a canonical unit to here, the group for not transformations here. Okay, well, then the first observation we have is just a remark, is that so whenever you have this group, it is acting by transformations here. This is being lifted here, so you have the twistor fibers going into twistor fibers. And then the observation is that this side action, the canonical unit acting here, is acting by isometries on the twistor fibers. Okay? So the lifting is conformal in one direction, isometries in the fibers. Then using that, you can push the discussion forward to dynamics. And before saying more, let me remark something which you don't know, that in all dimensions, the group of isometries of HN, real hyperbolic space, has a canonical then into the next one, and so on. Okay, this is just because I put the usage in commons. Then we prove, philosophically, we prove that the conformal dynamics of the spheres in dimension less or equal to 4 embeds in the holomorphic dimensions of CP3. Let me make this precise. Okay? So take a discrete groups of isometries in 5-dimensional space, which could come from isometries in 4 dimensions, in 3 dimensions, in 2 dimensions, and look at the canonical limits to PSL4C. Look at the limit set in S2. This is the usual definition. You look at the other group acting in S4, and you look at the foundation points of the orbits. That's the limit set by distinction. And now look at the action in CP2, and look at the set of accumulation points of the orbits in CP3. Okay, then we call that lambda 2. Then using the fact that the action is fibers is negative isometries, it is a remark to have that to show the set of accumulation points in CP3 is just the lifting the inverse metric of the setting in S4. That's just a remark. And then what is not so trivial is that if the group you started with is statistic against the group of isometries mentioned for n equals to 4 or 2, 5, then the action here is minimum. That means every orbit is dense. However, if you started with a group which comes from the isometries dimension 3 or less, or which is not statistic dense, then the action is not minimal in the twistor fibers. It is horizontally minimal, which can be explained by saying that if you look at the twistor fiber, then the orbit of the fiber is dense. But if you just take one point, then no. Okay? For example, an observation, the corollary, almost corollary of this, is that if you start with fundamental root of a closed hyperbolic manifold of dimension 4 or 5, then it acts canonical on CP3 with dense orbits. Okay, that's one example. Let me move to another example. In CP1, we have the classical Schottky groups defined analytically, and the usual generalization in conformal geometry is that you take a sphere of dimension n, then you take spheres of codimension 1, which are pairwise disjoint, and you have what they call this ping-pong dynamics. Every sphere gives you an inversion. If you make inversion in the same sphere 2 times, you calculate it. But if you have several spheres, you can start playing, and each sphere gives you an inversion, then you have the other one, you look at the group generated by them. It's a very, very interesting subject, and in that case, the unit set is a campus set. Yeah, so here we have an image. So taking this as an inspiration, let's go to the complex setting. And in the complex setting, you can start with CP2n+1 of dimensions and take a projective space of dimension n in here. Then take a tubular neighborhood of it. And one can show that it is split CP2n+1 in two isomorphic halves. And you have many transformations interchanging the inside by the outside. So these boundaries play the role of mirrors in the previous case. In the previous case, the mirrors were spheres. Here, the mirrors are the boundaries of these projective spaces. And you can start doing something similar. Now take a finitely many disjoint lines. For each one, take a sufficiently thin mirror, where sufficiently has to be very precise what you mean. The idea is clear. You take a very thin mirror and look at some isometry interchanging the inside by the outside. There are many, like some big one for each mirror. And now this generates a group of holomorphic automorphisms. And if the mirrors are thin enough, one can show that this is a discrete group. And you have very, very beautiful properties. One can prove the following theorem that the group you get in here is discrete, the mirrors are thin enough. Then the region where the action is properly discontinuous is actually a fiber bundle over CPM with fiber 2n+2 sphere minus a counterstate. Then these groups contain an index 2 subgroup which consists of the words of even length, which acts free. We same domain of discontinuity, but the action is free. So you can take this subgroup and take the quotient, which is now a manifold, because the action is free, and one can show it's a complex manifold, which is a fiber bundle over CPN with fiber a connected sum of this number of copies of this product of spheres. And these complex manifolds have moduli, we have beautiful theory over it. For n equals to 1, the quotient of it corresponds to this pretzel filter spaces of pendulums. Now let me move those two were two famous examples, which were how we started into the subject. Let me now look at groups in general, and then I will focus on dimension 2. First, some examples, some cases in general. And let me say that there are somehow three philosophical lines of research that we will follow. The first one essentially concerns when we go to CP2. When you go to CP2, it is natural to look at all the theory in dimension 1 that we know and see how if it generalizes to CP2, or how it generalizes, or if it does not generalize, what happens. So that's a natural first thing to do. Also, another very important line of research is the informatization problem, which is, well, we know that in dimension 1 we have the human, Kleinian informatization theorem. So it is natural, it's a famous problem to try to see to what extent we can one say high dimensions. So we look at that problem in this setting. And our third source of inspiration was this celebrated Sullivan dictionary. What is that? When you have a model transformation, you can think of it, let me say, as a quotient of two polynomials of two linear maps. Okay. So polynomials of degree 1. And if you have one of them and you iterate it, it's interesting, but it's something very well understood. But so interesting thing in that case is to consider a number, say a finite number if you want, of model transformations and look at the group they generate, and those are the Kleinian groups that they are displayed. But on the other hand, you can consider a rational map of degree more than one. The lowest transformations are rational maps of degree one. Now you consider a rational map of degree more than one. This is no longer an automorphism, so you cannot consider they do not generate a group by iterating them, but you can look at all the iteration theory of rational maps. That's a very interesting dynamical system in this field. And you can ask yourself what similarities there are between the iteration theory of a rational map and the theory of Kleinian groups. And that's how Sullivan's dictionary came by saying that he somehow gave a frame of mind to think of this in a way, saying that every item you know on one side somehow corresponds to an item on the other side. And it's not a perfect dictionary, not everything translates, but there are many interesting things. So, for example, for Kleinian groups, there was a famous theorem, which was Alpers Weier's theorem, and asking what would be the equivalent for rational maps. That's how Sullivan came to his famous non-wandering domain theorem. Okay, so that dictionary has been a tremendous source of inspiration for dynamics in one dimension. Is there anything we can do in more dimensions? Because after Sullivan's dictionary, the iteration theory in several complex variables has developed tremendously. Is there something on the other side of the dictionary? Okay, that's something we can pursue. Okay, so these are the three lines, and let me say a few things about each of them. First, let me say that a key concept in model work is that of the limit set. So in really complex and quantitative hyperbolic geometry, the limit set can be defined just as the set of population points of the orbits. So it would be natural to take this as our definition. But this is not a good one in general. Because in all these cases, the limit set has very nice properties, dynamical, and one basic property is that the action on the complement, this property is continuous. So now you can give any definition you want. The question is if it leads to anything interesting. So this definition doesn't seem to be good in our setting. And an example which essentially is due to Ravi Kulkarni is he gave it in a slightly different setting, but it was the same. This is completely analogous to Kleinian. And take this matrix or the equivalence class of this matrix that you can recognize it because here is elsewhere. So you have these three eigenvalues, and then you look at the exactly group it generates predicted transformations. Then it's an exercise to show that you have one point which is attractive, one point which is repulsive, and one saddle point. And then if you look at the accommodation points of the orbits, the accommodation points of the orbits are exactly the 3 points. That's easy. So you can say, well, that's my limit set. But then if you look at the lines spanned by the vectors E2 and E1, or E2 and E3, E2 corresponds to the saddle. If you look at these accumulation points, if you look at these two orbits, then you can show that the action of the complement is not properly discontinuous. So you have to remove at least one of these lines in order to get something which is actually properly discontinuous. So it's not what should be the definition. That's still something that there's not a unique answer. You can give several definitions, each one has properties, so it depends what you want. One definition is the one that Kulkarni gave, which applies in a very, very general setting. Somehow it's too general. Well, and let me say that the difference with hyperbolic groups of for example, in very complex or dynamic hyperbolic space, is that in all those cases you have this convergence property. That if you have any sequence of elements in this group of isomorphies, then the sequence either contains a convergence of sequence or usually outside of a point, it converges to a constant map. Okay, that property is very, very important that it allows you to do many things. In particular, the fact that the limit set is independent of the choice of orbit, that the action is minimal, many results come from this fact. And so there's actually a concept of what is called convergence groups, which groups will look at this. And in the projective case, you don't have this. And that makes life much more complicated or interesting or whatever you want to do. So it's a different setting. So Kulkarni proposed a definition that was in our case. Here a definition a limit set that is closed and an environment and which gives you, it grants you that the action of the component is properly discontinuous. Now, this definition, which I'm going to be on, somehow is too dry. So, in general, perhaps it's not good enough. But we can show that for two-dimensional complex relating space, this is a good definition. In higher dimensions, we know that it is not in general a minimum set. There are more refined concepts of limit set, for example, coming from using the Cartano composition theory. But to dimension two, the dynamic to be this good. So then just a name, we define a complex Kleinian group to be a discrete group in here, and we ask to have a region here where the action is properly discontinuous. Now, given a sketch group here, you can look first, this is Kulkarni's definition. You can look at first at the points, the closure of the points where the action, where you have infinite isotropy. You remove that, and then you look at the points in the complement, and you look at where they accumulate. Then you remove the two of this, and you look at compact sets in the complement, and you see where they accumulate. You take the union of these three things, and that's the definition you could carry in it. Okay. It's closed, it's invariant, and the action is properly discontinuous in the complement, and you have always a fundamental domain, and you have several nice properties.
So in your example where you have the 3-point accumulation set.
Let me go to this. Yes, because I think I will answer it. So let me start with the simplest examples. Take one transformation and iterate it. Okay? So we know in the classical case that we have essentially 10 types of transformations. I mean, every 2 by 2 matrix can be diagonalized or can be taken to this form. This corresponds to the parabolic elements. And this, if the norm is 1, these are the elliptic elements. If the norm is not 1, these are loxodonic elements. Okay? And then in the first case, you have a unique fixed point, and that is the limit set in this case. In the second case, you have 2 fixed points. In the elliptic case, 2 fixed points, and you have another dichotomy. Either the group is finite or not. If the group is finite, the limit set is empty. If the group is infinite, the limit set is empty. And in the third case, you have exactly 2 points. One is attractive, one is repulsive, and the limit set is this union of these 2 points. That's classic in CP1. Let's go one dimension more, or to any dimension you want. You can go, the dimensionalization goes in all dimensions. Take matrices here, and we can say that if the element is elliptic, if you have a link here which is diagonalizable, and all eigenvalues are having only 1. In that case, the limit set of those defined is either empty or the closed CPM. The element is parabolic if you have a lift which is non-diagonalizable, and you have all eigenvalues have no 1. In that case, you can show that the limit set consists of exactly 1 projected through space. And In the third case, is going to have only some eigenvalue of the one. We call those loxodromic. And in that case, you can show that the limit set consists exactly of two subspaces that can have different dimensions. So when you are in CP1, your only possible subspaces are points. So you have 2 points. Here you can have 2 subspaces of different dimensions, but you have exactly 2 subspaces. So this extends the usual definition here, and also the usual definition for complex hyperbolic groups. Now, as a second example, let me consider exactly groups of complex hyperbolic isometries. Okay, so this, you can think of this as group of isometries of the space. This acts on CPN, preserving a set above of points whose homogeneous coordinates satisfy this condition. This gives you a ball with projective space. That ball, you can equip it with an internal metric, and that becomes a model for complex hyperbolic space. And the action preserves the ball and also preserves its closure. The boundary still. But you can think of it as the sphere of infinity of complex hyperbolic space. And now every group here, you can define a limit set in different ways. You take a complex hyperbolic space, and you look at the accumulation points of the orbits. The orbit is accumulated in the sphere, and that is the chain-driven limit set, defined in the analogous way to the usual limit set. But if you look at the action on the projective space, here you are looking at the action on the inside the ball. But you have a group of projective transformation. So you could see, you could ask what is happening with the action everywhere, elsewhere, in the component. And then, well, you have this the limit set that I just defined. Okay, so the Kleinian limit set that I just defined. And then, in this case, well, as I told you, we don't have this convergence property. So we introduced a concept that we call pseudo-projective maps, which is just this group is to take automorphisms C to Cn plus 1 and Cn plus 2, and you take the projectivization of the automorphism. That is the projective group. Well, instead, you could take any linear map, remove the kernel, and you projectivize what you get. That's what we call the group of pseudo-projective maps. Okay? And then using this group, one can study, one can say things about this one. And one can do the following theory. We start with a group of hyperbolic isometries, complex hyperbolic isometries. And so you have the limit set, which is the limit set, which is a set of accumulation points in the sphere of infinity of the ball. So you have a set in the ball. For each point in the sphere, there's a unique hyperplane complex rated hyperplane, which is tangent to the sphere at that point. Since the limit set changing, the limit set is invariant, well, the union of all these hyperplanes is an invariant set. Then one can show that this set, the union of all hyperplanes tangent to the sphere at a point in the changing of the limit set, is the Kleinian limit set. Okay. And one can show that the complement is the region where the action is equicontinuous, and also this is the largest set where the action is properly discontinuous. So this is a nice example for one can work specific.
So can I ask a question?
Yes, please.
So like in complex hyperbolic space, the boundary, there's no problem defining the limit set when it factors through EU and it's only when you want to think of how it's acting the full CPN that you need to like fatten up the limit set.
No, if you look at complex hyperbolic space.
Like it's just the regular accumulation points at X.
Yes.
The population continues in the
Yes,
constant that on the boundary.
Yeah,
So if you want to think of that inside CP and
CP,
n or n minus 1, you need to make a bigger limit set to get the population continuous.
no, I mean, you have a complex hyperbolic space as a usual concept to change the limit set, which is you can take as you have several models for complex hyperbolic space. If you take the ball model, you have the boundary, and then the changing the limit set lives in the boundary, which is the sphere of thinking, so to say.
Right, and the group will like properly continuously on the complex hyperbolic space and the boundary minus this limit set, but it won't act properly as continuously on CPN.
No,
So you need to add more to, that's what you're doing, you're adding these tangent nodes to these.
okay, so for example, in the case of CP2, okay, so you have a four-dimensional ball with only a three sphere inside the ball. So the chain limiting inside will be contained in that sphere. But it can be the whole sphere or not. It can be a subset of the sphere. So if you want to see the action beyond the sphere, then if the limit set is everything, you can show that the action on the complement is minimum. But if you have, for example, a group whose limited set is not the whole sphere, then what happens outside is very intriguing. We understand something, there are many things we don't yet understand. That answers you? Okay, thank you. Okay, so in coming to complex dimension 2, one can say several things. Firstly, the Kulkarni limit set always contains at least one projective line. Now, the number of lines, so in the classical case, the limit set always consists of 1 point, 2 points, or infinitely many points. Here, it consists of one line. We can have 2 lines or 3 lines, but if it has more than 3 lines, it has infinitely many lines. Now, here you can also look at lines in general position, because you have many examples in which you have infinitely many lines, but all of them pass through one point. So you can look at how many lines you have in general position. In general position, you can have 1, 2, 3, 4. You have more than 4, you have infinitely many lines. And we have now the complete classification of where groups with 1 line, with 2 lines, with 3 lines, with 4 lines, and so on. Also, one thing interesting thing is that if you have isolated points, then you can have at most 1 isolated point. There is not example where you have 2 isolated points in the limit set. You have only 1. And if you have 1, then the limit set is 1 line and 1 point. Okay? And that's also, we have classified that. And if the number of lines in general position is at least 2, then the Kulkarni limit set is a union of lines, and the closure of the union of all these sets. And I'm forgetting what this was going to say. So if you have 3 or more lines in general position, then the limit set is a union of lines, and you have anything in many of them. And let's say more. So first making a kind of dictionary between dimension 1 and 2. So in dimension 1, we know that the limit set has 1, 2, or infinitely many points. Here is what I said. If you look at the complement, the linear of the discontinuity can be empty. It can have 1 connected component, 2 connected components, or infinitely many connected components in dimension 1. In our case, it can be empty. We have 1, 2, 3, 4 components. We have examples of all of this. We have examples with infinitely many components, but we do not know if these are real cases. So these are real cases, we don't. We don't know. The definition, the group is elementary. The group is elementary, the limit set has finite granularity. We define that the group is elementary, the limit set has finitely many lines in general position. If the group is non-elementary, then the limit set is the closure of the set of fixed points of the oxymorphic elements. In our case, it is non-elementary, then the limit set is a union of lines, and it is the closure of the set of invariant lines of the positive elements. So this is another. The complement is the largest set for the action is probably continuous. Again, if the limit set, all these 3 conditions are for the group is non-elementary. In that case, the complement is the largest cycle reduction for discontinuity. This is the region of discontinuity, this is the region of discontinuity, or equicontinuity, the reaction is minimal, and here the translation is that if there are no projections to the spaces we find according, then the action on the dual complex space is weak. On the dual projective space. Now let me move to the differentiation problem. And let me just go over for surfaces. There's a famous theorem by Seade, which says that if you have any compact complex surface, complex analytic surface, which has a projective structure, then it is either complex hyperbolic or complex affine. Okay? Well, let me give a definition. If you're a former student, we say that a group here, which has all properties continuously on some open invariant set CPN, which can have many components. Well, we say that if there's one component which is invariant and has compact quotient, then we say that the group is quasi-compact or compact. Okay? That's a definition. And then we can go through the following. If you have such a group, then it is either complex hyperbolic or virtually complex affine. And if moreover it is not virtually cyclic, then we have these conditions. That the concurrent set is the largest set of reaction is properly discontinuous, and if gamma is not a fundamental group for primary various surface, nor a finite extension of the fundamental group for a global surface, then this is also really continuity. And then we give the full classification of the open sets that can appear this way. This CP1 minus 1 line, CP2 minus 2 lines, minus 1 line and 1 point, minus 3 lines, and so on. So these are the open sets that can appear in such a setting. But you can have a group of projective transformations, which have this as an invariant set with compact quotient. And then we also give the classification, let me call it classification of the quotient spaces, and the second classification with quotation marks, because one of the items is complex hyperbolic manifolds. We are not classifying them. I wish so these are the types of compact complex surfaces that arise in this way. So you have a complex torus, or a primary surface, covariant surface, a torus, and also co-surfaces. A torus, in our case, if the region of discontinuity is this, then you have a node surface. In this case, okay. So this gives you the type of surfaces that can appear as a quotient of a discrete group acting properly discontinuous on some invariant set in CT. Now, just as a remark that comes to what we spoke before, if you drop the quasi-compactness condition, then this becomes far more interesting and we know very little yet. Well, let me come finally to the Solomon dictionary. What time is it? 4:15. So I still have 15 minutes. Okay. Okay, so about Solomon dictionary, because the dimension one is a dictionary between iteration theory of rational maps on CP1, and finally the numerator, non-elementary Kleinian groups. Then you have the concept of the limit set, Juliet set, which corresponds to the limit set, and the component, the factor set, corresponds to the region discontinuity. Going to one more dimension, we have first items, some items, we are trying to do something stronger. We are, I think next year we will have a more definite theorem. But you can look at rational maps, item CP2, will be at least 2. In this area, you have origin generator, non-elementary projective groups. You have the Julia set defined this setting, and the factor set. And you have the limit set and those are our basic objects. And then The following term is essential to what follows, or what we do, is that whenever you have a fixed number of generators, you can look at the space of all complex time groups with at most d generators. And then one can show that within here, the Kleinian groups whose Poincaré region of discontinuity is a complete Kobayashi hyperbolic space, is a Zariski dense open set in here. That's something we show. And well, and then in all these cases, the unit set is connected. And then with that, we have already some items in the dictionary. This is for rational, here's rational maps in CP2, here's Kleinian groups. And here the Julia set is closed and invariant, the unit set is closed and invariant. The Julia set is connected, then the unit set is connected almost always. So except when you have one line and one point. The Julia set is non-empty, the unit set is non-empty. Here we have this theorem that the unit set is the closure of invariant attractive lines of the absolute elements. And so far as we know, there is nothing known in design. Here you have the factor set is a complete Kobayashi hyperbolic space. The Kleinian region of the discontinuity is complete Kobayashi hyperbolic space generically. Factor set is Stein manifold. This one is generically Stein. This is pseudo complex. This is pseudo complex generically. And yeah, a crucial step for understanding this dictionary and so on is the classical understanding the non-generic phrases. And that's what we call the elementary groups. And especially interesting class of elementary groups are the discrete subgroups of the Heisenberg group. So you consider 3 by 2 complexes and matrices with complex coefficients, with 1 in the diagonal and ABC complex numbers, and you look at the discrete subgroups. Okay? Then all those discrete groups are elementary in our definition, and we have a full classification of which discrete subgroups you're going to get in that way. And we have a complete classification now of all the elementary groups. We are given Poincaré's volume, and so we have 7 over projects, and that's it. Thank you.